Hello everyone, I'm Quingbo. Today my presentation topic is fatigue-resistant node structure enabled by artificial intelligence. First, let me give you a brief introduction of background and motivation. So, inspired by the joint between the pedicle and the receptacle in sunflowers, which shows a high fatigue-resistant phenomenon under the cyclic loadings. So our motivation is investigating a method to design a fatigue-resistant node structure. But the difficulty is the typical deterministic fatigue design approaches usually involve very large computational costs because it needs to analyze astronomical number of possible node geometries. Here, our method is taking advantage of artificial intelligence approaches data analysis abilities based on very limited training data to construct the relationship between node geometries and their finite element analysis responses, then try to search for generating the high fatigue resistant node geometry. Before the deeper analysis, we need to know the mechanical properties of what we choose the material. Here we designed this dog-bone-shaped specimen according to the ASTM standard G638 and had universal tension tests on the MTS machine. At the same time, we used the DIC equipment to evaluate the full-field stride. We can see Fixie shows a standard Berto fracture of PLA material, and the low displacement curve and the stress curve also show this Berto behavior. By the way, the dog-bone shape specimens were manufactured by FDM 3D printing. The printing process parameter settings are based on our previous studies. Before the finite element analysis, the design method of sunflower-inspired node geometry should be clarified. Here shows the geometry generation process. In a 12 by 12 design space, we set the volume fraction is 15%, and this gradient descent strategy was used to generate the geometry shape. To avoid generate this zigzag shape geometry and keep the volume constant, we connected these middle points. After finite element analysis simulations, we found this geometry design approach will generate the stress concentration singularities. So to avoid this phenomena, we introduced the B-spline to generate the geometry shape with a more smooth edge. During the finite element analysis, even only need a very limited training data for artificial intelligence. However, there still needs a lot of computational costs. Compared with the stress concentration factor, the strain energy density is not sensitive to mesh size. And since the computational costs is related to the mesh size, so here we choose strain energy density as geometry's response. If the strain density over a given control volume reaches a critical value, the failure will occur. So the strain density depends on the material. Normally, we can calculate the critical volume based on Figure A, which contains common notches, such as sharp V notch, crack, and blunt V notch. But the problem is, for this non-constant notch, the control volume, this red area, is also non-constant. So it will be difficult to calculate the strain energy density according to the general control volume. There is a new idea. For non-constant notch, we can calculate the strain density in the area larger than the general control volume. Figure C and D shows the strain density calculation process. We calculated the different geometries SED values. Then these geometries and their corresponding straight energy density values will be used in the artificial intelligence training processes. This is the main architecture of a convolutional neural network. The convolutional neural network is one of the artificial intelligence approaches. Since the convolutional neural network is especially suited for analyzing the image data, so I translated the geometries to images first. Then the images and its related straight energy density values will be used as training data to train the convolutional neural network model. After different layers training, it can give a prediction for target object. The training layers consist of convolution layers, ReLU layer, polling layer, full connector layer, and so on. Each layer has a specific function. Through the connection of different layers, the image information will be extracted and the relationship between images and the straight energy density values will be constructed. We applied this trained convolutional neural network model into the geometry prediction under the universal tension condition and the in-plane bending condition separately. Figure A and D shows the data distribution of straight energy density. Figure B, C, E, and F shows the prediction accuracy of validation and testing cases. They all show very high prediction accuracy, which are bigger than 99.5%. From the prediction results, the corresponding geometries show a specific regular. The lower strain density value related geometry show high fatigue resistant behavior. We can search for generating some high fatigue resistant notch geometry according to these prediction results. According to the prediction results, we compared the predicted geometries with some standard notches, such as quad notch with a constant radius, sharp V notch, and blunt V notch. Compared their straight energy density values, we can see even though some predicted geometries have the same or low fatigue resistance with some standard notches, but we can still search geometry which has high fatigue resistance than all standard notches. And the predicted geometries fit our expectations. The computational costs are what we are very concerned about. Here we compared the straight energy density distributions of universal tension and in-plane bending conditions. They both show normal distributions. We also tried several prediction processes to study the relationship between prediction accuracy and training data scales. Figure B shows the convolutional neural network model can give a high prediction accuracy that's more than 80%, even if we only have 20% of total data. So we can define how many datasets are needed for training this convolutional neural network model according to these prediction accuracy curves. The approaches are related to the calculation time. Here we also compared the relationships between computational costs and trained data scales. This project has three main contributions. First, not a general straight energy density calculation method was used in finite element analysis simulations, but straight density values were calculated by new method also showed a deep correspondence with related geometries. And second, the convolutional neural network model predicted geometries showed a regular distribution. The optimal one can be predicted and showed a higher fatigue resistance than some standard notches. Third, Even only use small batch data to train the convolutional neural network model can obtain a high prediction accuracy. The computational costs can be adjusted by train data scale and the required accuracy. Well, this is all. Thank you for your attention.